presentation. So as the title is the same, and now it is the part 2. It is the same flow of the presentation. But I was thinking of, that is, if I could briefly just revise some of the concept in very in nutshell, like, so that our participants, they can easily relate, because I believe that it was on the first day, on Monday, and today is the Friday, so in between almost like 4-5 days has passed. So that if I briefly recap, then it would just help everybody to revise and to recap, even those who were not present the last day. So maybe it will be helpful for them as well. So with that, I'm playing that video once again, so that you can just easily revise the concept of the keywords which we started it in the last day, like multi-agent system, then cooperative control, consensus, distributed control system. Okay, the formation also. Let's see. This was the first experiment, that is, which we saw the other day. And in fact, that is, you can easily now recall that it was an example for the formation control, right? Where the 6 agents were like moving from one end to another end, making a triangular formation. And in this part, you will find there is one of the robots will become faulty. So it is simply just going out of the network, and the remaining 3 will still let us continue to proceed with the mission, right? So this is one of the feature called fault tolerance. Now the second one, it is on the drones. Again, it's a repetition. There are one new video also, which I will show you at the end of, this end of this presentation. This is the first part of the video. That is where I think you can easily recall, that is, we had 4 quadcopters, and it is only one group, right? And it is not only a formation control, it is a circular time varying control, because you can see that is all those quadcopters, they are drifting circularly on the same plane, right? If you could locate its graph on the top right corner, it is a MATLAB plotting of its like position, then it would be very more clear. And now you can see that is the whole assembly is linearly shifting from just one point to another point on the same plane. So it is called the formation tracking. That is as if the centroid point, as it's showing by the picture, that it is like shifting from one point to another, and at the same time the whole assembly was also following the centroid. And then in the second part, sorry for the wrong click.
The screen is not visible, sir.
Is it
Are
now
you
visible?
sharing a screen?
Sorry, is it now visible?
No, your screen is not visible.
Oh, I think when did it go wrong? Was it fine even a few seconds before? Hello?
Yes, pardon?
I mean, that is how long the problem, how long before the problem started? Is it
No, screen
immediately?
is not visible from the very beginning.
Oh, then actually, sorry, that is, I thought that is because there at the beginning there is no one mentioned anything, so I found that it was I thought it was going fine. So would you please just give me the access to stop share and start again?
No, no, it's all right, sir. You just proceed. You just share your screen and start. No problem.
I already shared, and in fact, this now the sharing option is deactivated. It's the same thing which
Okay.
happened last day also.
Okay.
Would you kindly just give me the access to stop share,
Just a
or
minute.
even the
Just a minute.
huh? Uh-huh.
Just a minute.
Yeah, sure. Yeah, I'm going to share the screen. And is it now visible?
Um, yes, sir. Yes, sir. Now it's
Okay,
visible.
I think that last time also it was like that only, but in between somehow there was a network glitch, maybe for which that is it went wrong. So I hope it is now like on the full screen, right? You can see the screen.
Yes, sir.
Okay, so I request that is the whenever that is if again it goes wrong, so you please feel free to stop me immediately, okay? Because from my side actually I couldn't figure out anything. So with that, I'm really like sorry. I apologize to all the participants because of this disruption. So once again, I don't know that is how much you have been able to follow. That is, but I at the beginning I didn't explain anything. So just the title. It is a part two, and then I was saying that if I recap briefly of the last day's content, then it would be easier for all the participants to relate. So with that, I played the videos and maybe that you couldn't follow. So once again, that is if you'd allow me to show the video. I'm just coming to the video directly. So this is one part where you can see that is the 6 robots are just moving on a particular pattern, like they are maintaining a trigonometric, it's simply a triangular pattern and they are moving from one place, like one side to another. So this is an example of
Again,
formation
it is not
control.
sharing.
Sorry, is it a problem again? I heard someone was saying something. Is it a problem again?
Yes, sir.
Is it going
Yes, sir.
fine? Okay, or
No.
is it a problem? So in this part, you would see that is just one robot which stopped functioning. That is because it is, you can think about either a network problem or a hardware fault. So the remaining 3 will still just continue the mission. So this is called the fault tolerance feature of the cooperative control. The next, it is another
Sir,
demonstration.
can you share your screen once because your screen is not visible, sir, again.
Oh, is it so? I'm really very sorry. That is,
Yes.
I don't know why it is happening, but it is already on the shared mode. That is as I started. Okay.
Now it is visible, sir.
Hmm. So, by any chance, you the first video was visible or not even? Hello, madam. Was the first video visible?
Yes. Yes, 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 yes,
Okay. So from the second one, it is a problem, right?
yes.
Okay. So just let me play the second one. So I hope this is now you can see this. So the first part of
Yes.
the drone experiment, where this is and the formation control. 4 drones are there. It's a square formation, but it is not a static formation. You can see that is as if that square is continuously rotating. That is as the drones are drifting from their place, and now the whole assembly is moving linearly from the left side of the room to the right side. This is called formation tracking. For better understanding, you can always look at the MATLAB graph, which is being shown at the top right corner. And in the second part, you will show that 2 groups would be there instead of one. Now, as you can see, we have 2 subgroups, each containing 3 drones. So as it is free, so you can think about that it's a triangular formation, and that triangle itself, it is rotating circularly. So that I think you can notice, and even it would be easier for us to mark the trajectory from the like, MATLAB graph, which is being shown at the left top corner. So with that, that is, I'm going to the main part of the talk. So if I just quickly just glance through the slides, then it would help us to recall the things which we learned the last day. So first of all, we learned it's a leaderless consensus. So consensus means all the agents or the system will come to the same point. If there is a leader, then it will just converge with the position of the leader, and the agents cannot work isolatedly. There must be some communication between the agents. That means that each one must share its its own state, maybe the position, velocity of the acceleration with the neighboring agents, so that each agent knows or can calculate the error with respect to its neighbors, and accordingly it can take an corrective action. Okay. After consensus, that we can move on to formation control, that you have already seen in the video. There is formation control means it is a coordinated motion maintaining a particular geometric shape. In this particular picture, that is, I have considered four elements or the four systems, so they can form a square formation. And if the centroid, which is also called the leader or the target, if it slides or if it moves linearly, then the whole formation assembly will also move accordingly. Okay, that what we have just seen in the video. Then here also the agents must be this interconnected through a network, because otherwise synchronism cannot be achieved. Then last day I also mentioned that is this the main motivation behind this cooperative control is the nature synchronization. That is where we saw these few examples of the birds flocking together, and then the motion of the bees, this motion of the school of fish, and the ants. Like, there are just many nature swarms. Then the main question that comes, the main theoretical question, how to model a multi-agent system. There, I started with this slide, that is how to first model the interaction among the agents. So there, if you consider three like agents, for simplicity, I have considered only three agents, and they are connected bidirectionally. So the each of age has an weight, that is where, since it is a bidirected graph, or sometimes it is also called undirected, so the weights would be of the same. So you can say that it is all the synchronous weight, say the full, like, sorry, the symmetric graph. So it is a ij equals to AJI. And accordingly, that is, you can remember the Laplacian matrix is the subtraction of the in-degree matrix minus the adjacency matrix. Now, as an example, that is here we learned that is for this particular graph, the in-degree matrix is a diagonal matrix containing the element 2, 2, 2. Why? Because each node has two incoming nodes. And if you see the adjacency matrix, then all these elements, A1, 2, A1, 3, A3, 1, and then like 1 2 2 3 3 1, and then 2 1 3 2 and 1 3, all of them are 1. So accordingly, this is the adjacency matrix. As a whole, this is the Laplacian matrix. And I mentioned that for bidirected graphs, the Laplacian matrix is always a symmetric matrix, and not only symmetric, it is a symmetric positive definite. If you have a leader with that, then of course the element or the agent which is pinned to the root node or the leader, then it will have this one more weight. That is, the weight will be increased by one, provided all the edges are simple and they have their weightage equals to one. And then the positive semi-definite matrix will become positive definite, but maintaining the symmetry property. That is the difference. So here, why I'm introducing the root node? Because ultimately you're reaching consensus means everywhere we would like to achieve a leader following consensus. That means the leader must be there. So root node plays the role of the leader. So it must be pinned to a agent. So that means there would be a non-zero weight. So accordingly, the pinning matrix P will come into the picture. So that's why that is I kept this slide from where you can easily distinguish between the leaderless and leader following consensus. Not only that, as the graph is concerned, how the difference will be there. So now I believe it would be clear to all of you. Then it is just two simple examples I have considered here. Suppose security surveillance, four drones are mapping one particular area, and they are talking to each other, or they are connected to each other following this particular graph. So the Laplacian matrix will be what I have just mentioned on the graph. Here, since no leader has been taken, so no question of the pinning gain matrix. On the contrary, if you consider this example where the four choppers are on a mission, are engaged in a mission, and then one, the bigger one is a leader, and the remaining ones are the followers, where the leader is connected to all three followers. So now the Penningen matrix will be a diagonal matrix of all three diagonals being filled with ones, and the adjacency or even the normal Laplacian matrix that will be that which is like D minus L, it would be simply this one, but where I'm hovering the mouse. And then here you can distinguish that is a L suffix P. L suffix P means here this is the shorthand notation for L plus P. So this is the Laplacian matrix plus the Penningen matrix as a whole. This is the whole one, which is the Laplacian matrix for this one. But please just look at the difference, that is it is not symmetric, right? Here this matrix is not symmetric because this is an example where the edges are not bidirected. So it is an example of a directed graph, and accordingly the symmetry property is lost. Okay. Then coming to the main question, that is how can we model a multi-agent system, and especially that is how can we model a multi-agent system using a graph theoretic approach. Why do we take a graph theoretic approach? Because here if you just model a multi-agent system as a graph, then you can easily like detach the agent part. I mean, you can easily detach the system dynamics from the network properties. So as you can see in this dotted block diagram, that is this whole red one, it is a combination, or it is a stacked portion of all the plants. So the M has been repeated n times. If you consider, suppose if it is a double integrator or single integrator agents, and if you had there are 10 number of agents, so these blocks simply means 1 by a square, 1 by a square repeated up to 10 times. Okay. And then the whole graph, the network part, is being represented by or characterized by its Laplacian matrix L, and accordingly this whole blue dotted box, it mathematically represents the model of a multi-agent system. Okay. Then the next question is that we have to always design a control scheme. Here I'm very sorry for this typo, it must be Amy. So then two type of distributed control schemes we discussed. One is state feedback based, another one is output feedback based, right? So as there also there is, I mentioned it's a link with classical control system. That is when we learned undergraduate control system, there we used to rely on the output feedback, like whether it's a compensator or it's a PID controller, always we use the output feedback, and in most of the cases it is out immunity negative feedback. When we that is go into the second control course, in some universities they offer two control courses, or even the universities where the UG people have only one control course. For them, there is those who have the control specialization in their PG curriculum, and there is this advanced control courses are taught, and where the advanced control start with modern control. So the first topic that is taught in the modern control is the state space analysis. So the state space analysis gives us the advantage, that is instead of considering only the output feedback, if you can also take the feedback of the other variables of the system, then you can always have a better control or better grab on the system. So that is the main difference between the state feedback control and the output feedback control. Now, the configuration of a distributed control means, as I just mentioned, it can be state feedback based, it can be output feedback based, but in any case, the design of the control law will depend upon the agent dynamics and the graph properties. Okay. And the major cooperative control objectives, which we also discussed the last day, the first two are the most important one, or even the first two necessary things that we'll have to always achieve is to ensure the stability of the overall network system, and then to ensure so that the agents reach consensus of the formation. That is the main objective, right? But other than that, whenever you think about the practical implementation or the real system, so always there would be some model uncertainties, noises, disturbances, communication issues, as now it is not only the agents, and the interaction is also of huge importance, and which is being possible only because of a network, right? And as the network is there, so of course the communication and networking issues will be there. And last but not the least, there can be loss of agents as well, as we witnessed in the first video. So the other objectives are also something which we'll have to take care during the controller design. But in this particular talk, I have considered the like first two because they are the major things, and the remaining ones can be worked upon as the add-ons. Then this also I explained that the first thing is that these distributed state feedback control protocol, where you have the multi-agent plant. The green box represents the network part, okay, and in the feedback path we are using this CK, where the C, or even that you can read it as sigma. I'm sorry for the typo, but both thing is it is the tuning parameter, which is there. It's simply a positive scalar, and K is the main component, which is the state feedback matrix that we'll have to design. Okay. So this also, it has a direct resemblance with the classical feedback control, which also we discussed, that is in case of classical control scheme or even the classical modern control. That is, we read it as the state feedback control law U equals to R minus Kx, where Kx, it is mean that is K is the state feedback gain matrix and X is the vector which contains the states. For a double integrator system, you can easily think of that you have two states. One is the position, second one is the velocity. There, if we can design two K values, K1 and K2, and then it would be R minus K1 X1 minus K2 X2, right? In this way, we design the state feedback controller. And the same thing can be extended to the multi-agent setting, with the only one difference is that designing the K, while designing the K, you have to be really careful whether that K makes the multi-agent plan stable. Why? This problem is not very trivial, because when we deal with the classical control, there we are like there the problem is controlling only one plant, but now here we have multiple plants together, and that too they are not isolated, they are interconnected. Okay, so that network part is also included. So now our plant doesn't mean only the M, the L plus P block is also there. So the state feedback control protocol, or rather I must say distributed feedback control protocol, must consider the presence of the network as well, and accordingly we'll have to decide. So this also, that is we discussed, that is how we can think about a distributed state feedback, where if you consider three agents G1, G2, G3, each one of them has the input U1, U2, U3, and then the state X1, output Y1. Similarly, for the other two agents, it is X2, Y2, and then X3, Y3. So how can we write the control protocol? So for the first one, if you notice, or if you look at attentively, then U1 equals to the K, the state feedback gain matrix, which we'll have to design for this multi-agent system. And then this K will be acting on the relative error compared to our classical control, or even what we learned earlier. That is, U equals to simply R minus Kx, or which is the relative error. And now that is, you don't have only X, but rather here we are calculating the error with respect to the neighboring agents. So that's why here now that instead of one single X, it is X2 minus X1, that is the relative error with respect to the second agent, and then X3 minus X1, the relative error with respect to the third agent. And of course, R minus X1 will be there because with respect to its own referent, that is the absolute error, must also be taken into account. So as a whole, you have this A12 into X2 minus X1 plus A3, A31 into X3 minus X1, A31 or 13, both of them will be the same, because here we are considering a bidirected graph. So anyway, what you can see, that is this cooperative control law in the, when it is based on state feedback, then it is actually it is the relative error with respect to all the agents. So in a compact form, we can represent the control law in this. That is Ui equals to K into the first term Aij into Xj minus Xi. That is, you can read it as the summation of or the total relative error with respect to the neighboring agents, and plus pi into r minus xi, that is the absolute error with respect to self. Okay, why we need a summation? because here we are dealing with a multi-agent system. So for each agent, that means for suppose I equals to 1, 2, 3, you can write down the control law as I have written for these three agents separately. Okay, so this is the compact form. We need to know the compact form so that whatever may be the number of agents while like writing it or while expressing it or even while we will simulate it, you can just do it in a very comfortable manner. Otherwise, you will have to like develop the controller by each and individual element, so which would be just quite hectic. And this aij, that is the weight of the edges, or rather this is the entries of the adjacency matrix. Simply, that is, you can think about that aij equals to 1 when the nodes I and j are connected, and it would be 0 if they are not connected. Pi is the pinning gain. Say, for example, in this particular case, the root node or the leader is pinned to the first agent. So that's why this is P1. So P1 equals to 1. But the P2 and P3 will of course be 0, because at least in this particular case, the root node is not attached to the other two agents. Okay, so that is the interpretation. Then after that, we also learn the distributed output feedback control, where compared to the last configuration, it is now we are using the output. Okay, so the error is in the sense r minus y. Of course, the network part will be there, and we are using the dynamic output feedback controller. And if you would like to write its expression, then it would simply be ui hat of s equals to this whole thing. Here also, that is maybe that is this mathematically it look like very clumsy or complicated, but it is the same thing which we wrote earlier. It is only the difference is that instead of the relative state error, now we are using relative output error, because this is now output feedback based. So if you see or if you read out the term, it is the same thing. That is aij. Earlier we had aij into xj minus xi. Here we have yj minus yi. But why the extra terms are appearing? I have used that is the y hat, because now they are Laplace quantities, and since they rely there the independent variable is s, so that's why in bracket I have put s, and there's y small notation I have used here, so that's why I used the extra symbol hat to denote that it's a y hat, means it is a Laplace transform of the real time signal y of t. Okay, other than that, that is this pattern is exactly the same. Only the difference is that this controller has been expressed in the frequency domain, and also it is dependent upon the output feedback, not the state feedback. And lastly, here we are using a dynamic control scheme. So this controller ns is a transfer function. No longer it's a static gain. Like earlier we had a static gain where this is a k, simply a static gain, but now it is no longer a static gain. It's a transfer function matrix. Okay. So while just we will go to the design part, we'll have to learn that is given a multi-agent system. That means the agent dynamics M is known to us, and the network part L and P, those matrices are also given. Then how can we decide or how can we design this N of S, right? That is actually the design problem. So the prima facie, the first rule should be that is the NS, it must be asymptotically stable. So theoretically, we write that it must belong to this space RH infinity, and the C or the sigma, I mean here, it is the scaling quantity or the tuning term, which must be positive. Okay. So gradually we will like dive into the theoretical part, that is how we can design, but that too, that is in a very like the short manner, and I will only show you the main glimpse so that it doesn't become too much mathematical. Then this diagram can be rearranged into the following fashion. Why? That too I mentioned the last day, because we are usually like familiarized with this kind of block diagram where all the blocks would be on the forward path, and in the feedback path means it is simply unity negative feedback. Okay, so with that, here I explained, I hope you can remember, that is although here essentially like although here now we are dealing with three blocks, the multi-agent system plant, the controller block, as well as the network block. But still, by the means of chronicle algebra, you can club the network block with either the plant or the controller block, and then essentially it will become a a two block structure. Okay, one is the plant, another one is the distributed controller. Okay, if you see this diagram, then here I have clubbed the controller block with the network block. So as a whole, it represents the distributed controller. So this red block and the blue dotted block, they will constitute the closed loop control scheme, which you can easily just compare with the classical feedback control scheme. Okay, why this will be required? Because after this, when we think about any type of cooperative control scheme, two main things you have to always ensure. That is, first, this closed loop stability, for which you have to represent the whole system into a feedback interconnection of two blocks. It doesn't at all matter whether the two blocks are on the forward path or they are one on the forward path, one on the feedback path. Ultimately, as the stability question is concerned, you have to prove or you have to test the stability of a feedback interconnection, where you can think of that as if two blocks are on the forward path, even you can think of two blocks on the feedback path, or even one in the feedback path, one in the forward path. Okay. So with that, actually, I have, like, last day I didn't draw this block diagram, but I thought of that is, if I show this rearranged block diagram, it would be easier for all the participants to understand. Here you could see that is the first objective is only to maintain the closed loop stability. And for the stability study, we don't need to consider the external signal, I mean the reference and the summer. So that's why, as of now, I have removed the reference signal R and the summer also. And now you could see that this is an feedback interconnection of two blocks. You can even represent this into this structure so that it is now very clear to all of us that this is a negative feedback interconnection of two blocks. One is the M bar of S, which is the combination of multiple plants, and another one is the distributed control scheme, which I have denoted by N tilde of S, which is nothing but sigma into L plus P chroniker NS. Please don't get afraid about this, the symbol chroniker. Here, everything we are dealing upon, it is just the mathematical representation. Ultimately, you have one large plant block and you have one large controller block. Okay. And as the stability question is concerned, you have to check whether the feedback, negative feedback interconnection of these two blocks asymptotically stable or not. And the second objective is to show whether the steady state error is going to zero. Why that is required? If we could prove that yes, the steady state error will go to zero at t tends to infinity, that means we are discussing everything in asymptotic manner. So then it will imply that, as I have written in the blue color, that limit et tends to limit t tends to infinity et 0. Here e means r minus y, so you can say that is the y will track r. Okay, I hope you can remember that is last day I said this also, that is this consensus. You can think about that as if multiple systems are going to track one common reference. So that is nothing but the multi-agent system or multiple system tracking the same command, or which usually we call consensus. Okay, that means reaching an agreement or reaching the same state, or here they mostly say state of the leader, which the leader is represented by a signal, because always, whether it's a position or any kind of thing, that you have to like apply as a reference signal. And we want the output y. Here you can see this y is a bold letter, so this is not a scalar. So this y means it's a vector which will consist of y1, y2 up to yn. That means the output of all the agents, and we want that is those output will reach the r. Okay, so in that way, I hope that is now it is pretty clear to you that is what are the main objectives that we are looking for, and also the way how we will approach. Because so the first case, to prove the objective one, we have to look into the feedback interconnection, and then whatever theory known to us, we'll have to apply to check that whether, or especially it will help us to design the controller, so that finally we could prove that the feedback interconnection of M bar of S and N tilde of S is as remained asymptotically stable. And while the doing the second objective, it is simply here, that is, we will be applying our classical control formula. That is, you please write down the error dynamics. As I have mentioned, in this particular case, the error I have represented by the variable xi. So the xi of S and the mapping from the R to xi, it is given by this transfer function matrix. Here, please note it that it is no longer a transfer function, it's a transfer function matrix, and which, or nothing but the error dynamics if the error dynamics is asymptotically stable, and which is being ensured by objective by fulfilling objective 1, and then after that by applying the final value theorem, you will have to show whether ESS is a zero vector or not. Okay, that is more or less the strategy or the technique by which any type of cooperative control succeeds. Here again, I would like to mention that is in this way, it is much simpler compared to the many other ways which are there in the literature, and the fact that here we are dealing with all the this linear systems. Okay, even if the plant is non-linear, I'm going to show you that is we can apply a feedback linearizing controller so that the a non-linear plant, say for example a UGV or a UAV, that can be first linearized or it gives a reduced order linear mapping, and then we can apply or we can design a distributed controller keeping ourselves in the linear domain or in the S domain, compared to if you use the other like nonlinear cooperative control techniques, then those calculations, I mean the theoretical steps, it's much more rigorous. The calculation, implement, and the apprehension, the comprehension, and also the implementation are really very challenging. So in that respect, yeah, if you follow this technique or this kind of mechanism, then where we are simply extending our classical control concept into the multi-agent framework. So where I'm not claiming that is this method can be applied to all type of multi-agent systems, which is certainly not. But for a major class of multi-agent systems, you can apply this kind of frequency domain-based approach as well. So let's see like two small examples. These are not case studies. We ultimately at the end of today's talk, I will show you the case studies on drones as well as two-wheel mobile robot. But as of now, two synthetic examples. One is contains the single integrator, another one is double integrators, which is going to come after this. Here you can think about that is I have considered three single integrator agents. They are bidirectionally connected, and we wish to design a distributed controller for achieving the leader following consensus. Here, the leader of the target has been labeled by the zero node. So the plant MS is 1 by S. The NS, the controller, I have designed by applying passivity theory. Please don't worry. At this moment, I'm just not going into the details of passivity theory, but there are one other, which is the negative imaginary, that I'm going to discuss because that is one of the main part of this presentation. But anyway, for the time being, if you assume that there is a theory called passivity theory, and which says that a negative feedback interconnection of a passive and one strictly passive system always remains asymptotically stable, and that theory can be utilized in this particular case to design a controller. So this 1 by S, it follows one particular system property. Then I have exploited that system property to find out a controller of the following a same but a restrictive property of that class, so that their negative feedback interconnection becomes asymptotically stable. Okay, so here you please don't worry about the passivity theory, just you read it that a negative feedback interconnection of one class of system called passive and another subclass or like subset of that class, you can think call it as strictly passive, they are always asymptotically stable. Okay, and here I have used the undirected graph. So if you assume or if you consider that is okay, our objective one has been fulfilled, the second one is that we have to really check that is whether the second objective is fulfilling. That means whether the steady state error will go to zero or not, because otherwise the consensus won't be achieved. Let's see how we can prove that one. So again, I'm just starting of using following the way which I mentioned in the slides, 2 3 slides before. That is, you have to first mention or find out the expression of the error dynamics, and then you simply that is go for you apply the final value theorem. So if you see that the plant is 1 by S square, the controller is an SNI controller. So being SNI, it will always be asymptotically stable. So N of 0 will exist. So eventually, after this putting all the limits, the steady state error will be 0, which will ultimately imply that is the all y will reach the r asymptotically. Okay, this proves that the consensus will be achieved. Similarly, if you just take an example of double integrator agents, in the same manner it will go, but here we have to apply a different theory because double integrator systems are not passive, rather they are negative imaginary. This particular theory, I'm just going to discuss in a bit detail. So this is a new theory which started in 2008. I believe that is that it would be once I explain this, then it would be interesting for all of us. So if for the time being that if you assume that is okay, the theory is correct and I'm applying that result only here, then with that just platform, I'm just showing you the result that is provided. This 1 by a square is a negative imaginary system. And then that is I can easily think of a strictly negative imaginary controller having a negative definite DC gain. That means simply you can think about that this transfer function minus of s plus 2 by s plus 60, its DC gain, the zero frequency gain would be minus, right? How could you get it? Simply you put s equals to 0. Here, if you put s equals to 0, that means at the DC frequency, it would be minus 1 by 30. Okay. So that is the requirement, that if you have a negative imaginary system having the poles at the origin, then it can be stabilized by a strictly negative imaginary system having negative DC gain. Okay. And another difference with respect to our classical control scheme, that this particular configuration works with positive feedback, not with negative feedback. Okay. So there is the proof is also there. That is why does it work with positive feedback. And accordingly, here you just must have noticed that is this R, the reference quantity, is now not simply R. It is the minus of R. Why? Because unless you take the minus sign over here, then you cannot achieve there is a Y will track R. Why? Because here the error is going to be Y plus R, right? Because it's a positive feedback case. So even if E equals to 0, then what will happen? R plus Y will be equals to 0. So Y will be equals to minus R at t tends to infinity. So that even if everything works fine, the output will reach the minus of the reference. So that is the reason why you have to deliberately negate the reference signal, and then the proper true tracking will take place. Okay, so that is only the matter of concern here. Let's see in the same way, that is whether the consensus error will go to 0 for this particular case, as we are now dealing with positive feedback system. So the sign will be minus, right, instead of plus. So this is the error dynamics, the mapping from R to the xi. Here I have written r hat. Why? Because r hat is the minus of r, as we need minus r in case of a positive feedback scheme. And in the same way we proceeded for the single integrator case, now also it will be the same thing. That is, here we can see that is the ns, it would be asymptotically stable. So it would be in n of 0 will exist. And after putting the simplification and putting all the limits, the steady state error will go to 0. So it's a 0 vector. And then I think that this is the thing which I was explaining. So limit t tends to infinity, xi of t equals to 0. That gives minus of r, which means here the minus of r means the r hat, which is the actual reference, because I already mentioned that is for a positive feedback scheme. If you want to achieve the true tracking or the faithful tracking, you have to negate it is reference signal. So minus of r plus y equals to 0. So now the y will go to r. So this is the theoretically we can prove there is a consensus error will go to 0. Okay. So now I'm coming to the basics of negative imaginary system theory, because here this is why this is essential, because whatever video I have shown at the beginning, in fact, one more I will be showing you later, everything, the theoretical scheme depends on this particular system property. So that's why that is I cannot escape this whole theory, because otherwise it would be like too much vague. That is, I claimed so many things, but without showing you the theoretical background. So I like request all the participants to be like a patient for these few slides. I believe that is I have kept enough example that is from which it won't be, I believe that is it won't be very much tough for us to understand. Okay. And despite that it is like a new thing, so of course you may face some difficulties, please feel free to ask me. Okay. So if you take a look at the keyword negative imaginary, so the name itself will give you the hint and why the name has become negative imaginary. So whenever we talk about a transfer function, or even not transfer function, you just go back to your plus 2 level, like class 11 or 12, or even before that, when we first learned the complex variable. If you think about the complex variable z, which we can write that x plus iy. So the y is the part of imaginary part which is preceded by this I operator. And then in if you can relate that concept with a transfer function, that means suppose you have a transfer function, again it's a complex quantity, and with the difference being now it's a frequency dependent complex quantity, it can be always resolved into the real and imaginary part. So if we find that is the imaginary part, the value of the imaginary part or the magnitude of the imaginary part will remain negative for all positive frequencies, then that particular system satisfies the negative imaginary property. Okay, but with that, maybe you are saying that is what the speaker is like saying, it is not at all understandable. So let us see, that is it, what is the definition, and then I will be explaining the concept with respect to many examples. Okay, so theoretically or like technically we can say a transfer function m of s is said to be negative imaginary, in short ni, if its imaginary part is negative or even non-positive, because the zero value is also allowed for all positive frequencies. Okay, and it is said to be a strictly negative imaginary system if the imaginary part is strictly negative for all strictly positive frequencies. Now, I hope that is what I just said, that you can see it in a written sentence. So it would be now a bit more clear, at least how to read out the statement. But still, it is not clear to you unless I show you an example. Let's take a very simple example, a first order plant, that is k by s plus p. So here it is the loop gain k, and you have this only one pole at minus p. Okay. So if you resolve this transfer function into the real and imaginary part, it is the same thing. That is for all the participants who are not from control. You just think about that you have what we did in our that plus 2 level. That is, you have a complex quantity, and if it is in the denominator, then how to rationalize it? That is, you have to multiply by its complex conjugate, right? Both the numerator and denominator. The same thing I have done. If the denominator is p plus j omega, I am multiplying both the numerator and denominator by its complex conjugate, p minus j omega. And after that, if you go by, if you do a simple like calculation, or it is not even a calculation, it is just a simplification. So, and you can easily split the real part and the imaginary part. So what is now this imaginary part? K into omega divided by p square plus omega square, right? So k is a positive quantity, like strictly positive, p is strictly positive, and omega varies from 0 to infinity. So at omega equals to 0, everything boils down to 0. And for all positive omega, I mean the whole thing, it will be negative because it is preceded by a minus sign. So it satisfies the definition. That is, for all positive frequencies, the imaginary part remains negative. So that's why it satisfies or it exhibits negative imaginary property. But not only that, if you exclude the zero frequency, then for all strictly positive frequencies, the imaginary part remains strictly negative. So that means this system is not only negative imaginary, but strictly negative imaginary as well. This can be easily interpreted by its polar plot. So if the polar plot means it is like one type of frequency, like a response plot, but other than the Bode plot, because Bode plot, I think all of us know that is simply frequency response, that is log 10 omega versus the MDB. Here it's another kind of plot, which is the polar plot. So for the polar plot, you can easily check. That is, suppose you are given an LTI system and a CISO LTI system. If you is see the polar plot. Suppose you may not do by your hand, you can simply use the MATLAB to check its polar plot. If the polar plot remains in the fourth quadrant, or even third quadrant, or even the union of fourth and third quadrant, then that means the imaginary part, actually this is the axis, the passing through the, like this is the real axis, this is the imaginary axis. So this entire polar plot implies that is the imaginary part, it is negative, right? Excluding the zero and infinite frequency. That is the interpretation which says that it's a negative imaginary system. Once again, if you see the whole plot, this whole blue, there's the graph, then that is, this is the axis, this is the like the through zero, it's the real axis, and this is the imaginary axis. So the graph is fully it is lying on the fourth quadrant. So that means that is we are, and here we are not like deciding, or we are not talking in terms of the real part, but the imaginary part will solely be negative, right? If you exclude the zero and infinite frequency. So that's why by looking at the polar plot, we can easily decide or detect whether a transfer function is negative imaginary or not. Don't worry, I'm going to show you the 5, 6 more examples. After that, it would be pretty clear. If you also wish to know the phase angle contribution, then this definition translates into, that is, the phase angle contribution for any negative imaginary system. It remains in the range minus pi to 0, minus 180 to 0. For this particular example, since it is an SNI system, so it cannot be minus 180 degree other than omega equals to infinity. That's why I have mentioned that is phi of omega. It belongs to the open interval minus pi to 0 for all omega in the open interval 0 to infinity. Okay. Let's see a few more examples. I believe after that it will be clear to you. Now, this is one particular case, which that is at the beginning I was mentioning, that is if there is some zero value. So if you look at this polar plot and at omega equals to 1, the polar plot is touching the real axis. That means at that particular point, the imaginary part is 0, right? Here I have put an arrow. So at this particular point, which is omega equals to 1, then the imaginary part will be 0. So we can find a point where despite being a positive frequency, which is 1, the imaginary part is 0. So that means this system cannot be strictly negative imaginary, but this is, of course, it is a negative imaginary, because now you can see this is in the union of fourth and third quadrant. Okay. One more, this is also a transfer function which is Ni but not Sni. Why? You could locate that at omega equals to root over 8, we have a point where the polar plot is passing through the or touching the origin, right? So at that particular frequency, the imaginary part will be 0. So it is another example which is Ni but not Sni. Coming to the example which 1 by s plus 1, already we have theoretically discussed it in the previous slide. So it is an SNI system. You can also think about another one, a second order system 5 by s. It is simply a second order underdamped system. It is also SNI because other than omega equals to 0 and infinity, the polar plot touches nowhere on the real axis, right? And if you remember, there is the definition of SNI system, those those points 0 and infinity, they are excluded. This is also why, if you are really inquisitive about it, that is, we can remember that is for any real rational proper transfer function, the imaginary part will always remain 0 at 0 and infinite frequencies. So that's why when we define these properties to explain the imaginariness, we are necessarily will have to exclude the frequency points, the 0 and infinity. Okay. So that is something. And then after that, you can also think about another system which has a non-minimum phase 0. Still, it's a SNI system, 1 minus s by 1 plus s. I hope all the EC, the participants will be very happy to see it, because it's a very commonly used example of all-pass filter that satisfies the SNI property. And after that, even 1 by s square, 1 by s, 1 by s square, even 1 by s square plus 4, this kind of system, they are also that is fall in the category of negative imaginary system. But please remember that they are not strictly negative imaginary, they are all negative imaginary. Okay. And strictly negative imaginary property are also defined only for asymptotically stable systems. Okay. So then the key takeaway point is that this I explained to you, or I mentioned at the beginning, that is, suppose you are given an NTI system, you can easily find out the polar plot. If not by hand, you can always use the MATLAB. And then you check whether the polar plot, that means the Nyquist positive frequency branch of the Nyquist plot, whether it resides in the union of fourth and third quadrant. It can also touch the real axis. Okay. In that case, it will be an NI system. Its phase angle contribution will be in the closed interval of minus pi to 0. Okay. But it would be certainly SNI if you see the polar plot is not touching anywhere on the real axis except 0 and infinity. Okay. Then it would be treated as an SNI system. Now, that is, you can ask, that is, like, what was the motivation behind this negative imaginary system, or how did it come? So it has a very interesting history. As a negative imaginary system, it comes from the concept of positive position feedback control of flexible structure system. That is why that's to explain that concept. I have taken an example of a cantilever beam. So this cantilever beam, this is an example that is which it always gives a lot of oscillations, right? And it is also an example of a flexible structure. This, this cantilever beam, just a second. I'm on a meeting, okay? So if you see the transfer function model of a cantilever being, of course, it is not the ideal one. This is the approximated model. It is about the GS equals to the sum of all second order transfer functions of omega n I. But this is, I think, this pattern is known to all of us. There is a omega n square divided by a square plus 2 zeta omega n s plus omega n square. But here, since the vibration will have many modes, so that's why it has been represented by using the summation sign. Okay. This is particularly Ni. Why? Because individual component, that is for I equals to 1, 2, 3, that is each mode, omega n square divided by like omega n square I by this whole denominator. The each mode is Ni. And there is a property that is if you sum up the Ni component, then the sum of Ni transfer functions will also be Ni. So from that, theoretically we can establish that this is a Ni, but let's see a practical example. That means a practical value, whether how does it really look like. So these values I have taken from one of the survey papers of Professor Lanson and Peterson, who are the father figures or the like pioneers of this particular theory. Then you can look into that is this is the transfer function, that's 10 to the power 4 by this one, and then this is the weightage of sigma I. Here only the first 15 modes have been considered, and if you check the frequency response, the Bode plot, then this is the phase plot where we are just mostly interested to check whether the phase angle remains in the range of -180 to 0 for all positive frequencies. And here you could easily see that is yes, the frequency, or sorry, the phase angle, it remains in the range of 0 to -180 degree for all positive frequencies. Okay, so that it proves that it's a NI system. And this is also one of the motivation that if you have this kind of flexible structure systems, and this is then these kind of systems can be easily stabilized by using their position feedback and in a positive feedback mode. Okay. So that's why it is a theory called a positive position feedback. That was the one of the main motivation behind NI system. All the proofs are there in the paper, but here we don't need the proof. I'm just telling you the motivation. That is why he started with. So that's why that is when I will show you the major applications of the NI. It will start from the vibration control only. If you would like to know to other like simple examples, then always you can think about a spring mass damper system of this asymmetric configuration. Asymmetric in the sense in the middle there is a spring, but if you see the two extreme end, so there in one end you have a damper, the other end you have a spring. So this is called asymmetric spring mass damper configuration. This gives an NI system. Okay. But on the contrary, that is, if you would have taken that is the same thing on the both sides, then the configuration would surely become SNI. But anyway, this is an practical example of a NI, and the simple the Sallen-Kiel Opus filter. This is an example of a SNI. How? Because here you can see the polar plot is touching the real axis at a positive frequency other than 0 and infinity. Because if a polar plot touches at 0 and infinity, of course, that can be an SNI system, because in the definition, those two frequencies are excluded. But if it touches anywhere in a finite positive frequency, as is the example here, the case root over 12.5, so that means it loses its thickness property. So that is the reason why the first one is an NI and the second one is an SNI system. Okay. The major application areas, as I just said, that it starts with the vibration control, but it is not restricted to vibration control. There are in fact many. I have shown here only like 5 specific applications, starting from the flexible robotic arms, nano positioning systems, large space structures, control of vehicle platoon. There are others. Okay. And you would be very it would be very interesting to hear that during the last 5, 6 years or 7 years, the NI theory that has been widely applied the cooperative control. So that is one of the main motivation. That is why I also started working in cooperative control by applying the negative imaginary theory. And from my research area, that is, I'm going to show you some glimpse. Okay, so that was the primary motivation. So then here now that is I will ask you a question. That is so far what we have understood. There is this CISO definition, right? That is if you deal with a CISO LTI system, CISO means single input, single output, a scalar system. For that, you have these graphical tools available. That is given a CISO system, you can easily check the polar plot by using MATLAB or any other kind of software, and easily you can detect the property. You can conclude whether it's a NI system at all or it's a NI system, even it's an SNI. But if you were given a very complicated system, suppose if you are given a 10th order system or suppose the 20th order system, then first of all, it won't be possible to solve it will be very hectic or tedious to do all those calculations by pen and paper. So if you tell me that is okay, I have the MATLAB. So then for all LTI CISO systems, we can find out the NI property by looking at the polar plot. But what will happen if you are given a MIMO system? For the multivariable system. So in that case, the Nyquist plot, we cannot apply the Nyquist directly. Then how to find out the NI or SNI property? For that, we need a state-based characterization. State-based characterization means suppose given a multivariable system whose the state-based characterized, whose like state-based matrices ABCD are given to you, then is there any method by which we can test the property of a system? Yes, it is there. Suppose you are given a system M, which is finite dimensional square LTI system with a minimal ABCD. Here, the audience which are not familiarized with the control theory, please like don't get afraid about. These are like some of the standard assumptions that is which we need. For the sake of completeness, I have just mentioned all of them. But the core result is suppose the ABCD matrices are given, where ABCD matrices means that is if a system is represented by a differential equation, and then if that differential equation is represented by a set of all first order linear differential equation, then its form is written as x dot equals to ax plus b, where a is the system matrix, b is the input matrix, c is the output matrix, and d is the fit through matrix. So with that, so once a given a system, so you can assume that is ABCD can also be found by any means. Okay, so for those quantities, now the question is that how can we check whether a system is NI or SNI? Then for that, we use the SDP solver packages. SDP means semi-definite programming solvers. The MATLAB can do it. We have the other third-party plugins like CVX, Sedumi, Yalmib. By using these third-party plugins, I mean there are some commands which will run these non-strict inequalities. And then if it can give us a positive semi-definite P matrix, then we can conclude that particular system is NI. Okay. And then there is, if we know that the plant is a stable, then even that particular LMI is a non-strict LMI. It takes another form where this P candidate will become a positive definite candidate. Okay, so these are some of the things that is we at this moment that is you don't have to bother much. That is, if you work on this particular theory, then that is you have to learn all this lemma and the other results one by one. Here I am mentioning because so that is you must have a clear-cut understanding in your mind that is this theory is not only for CISO systems. It is equally applicable to MIMO, there's a higher order, and any kind of systems. Okay. And also, I'd like to mention that is presently whatever I'm discussing, it is with respect to linear time invariant system, but it applies to linear time varying as well as nonlinear systems as well. Those things are quite more complex. So that's why there is I haven't included the nonlinear or the LTV part in this presentation, but the theory has already been extended into those direction as well. Now, after this NI lemma, the situation will also come that is where you have to test the SNI property. So for SNI also, that is in addition to the NI lemma condition, there are some other conditions. If they are fulfilled, then we can detect or we can that is test. We will say that this particular system is SNI. Okay. There is also another version called strongly strict NI lemma. Why? Because it gives us a strong the strict inequality. Sometimes that is it helps us in designing the controller. I'm just giving like two simple examples which already I considered, but now I'm verifying the same example by this method. So this is the transfer function we have already checked earlier that it's an NI transfer function, but how to apply the lemma or how to utilize the lemma to confirm that yes, it's an NI system. So there I have applied this second, the corollary, the AY plus or A transpose negative semi-definite and B plus AYC transpose equals to 0. So for this particular plant, we can from the transfer function easily we can find out the ABCD, and for that particular ABCD, this Y has been like found by using the MATLAB software. Okay, so we can comment or we can conclude that it's an NI system, but surely it won't satisfy the SNI lemma because it will break this particular condition that MS minus. So this actually means that is the imaginary part has a 0. So this particular transfer function as is evident from the polar plot, that is at that particular at omega equals to 1, the polar plot is touching the real axis. That means there will be a 0 at that the imaginary part will contain a 0 at that particular frequency. Another example, which is SNI, that too we have already seen, that is this particular case, the second order under damped system, this being asymptotically stable, it's an SNI candidate, okay, and which is also it would be like approved by its polar plot. But how to check with the SNI lemma? The same thing, that is we can again use the MATLAB to check with those LMI conditions. LMI means linear matrix inequality condition, okay? And especially you might have seen that is in case of NI, it is not only the inequality condition, the equality condition is also there. That is, this inequality is the other one, AY plus YA transpose, but there is a equality constraint as well, B plus AYC transpose. And that is the reason why MATLAB LMI solver cannot be directly used for computing such kind of problems, because MATLAB LMI solver, it works only for strict inequalities. If it is non-strict inequalities or even the equality, then MATLAB LMI solver cannot be directly applicable. Okay, so that's why that is we have to use or then we use the MATLAB based other third-party plugins such as the CVX, Sedomip, and EALMIP. After that, I'm coming to the main part, that is the NISNI stability result, which will be used in the when I will show you the application for the drone as well as UGV. There, the internal stability result would be required. That is the main. It has like two cases. The first case is that if you consider the NI systems without any poles on the origin, it may have on the j omega axis, but not on the origin. In that case, the stability result would be, that is the DC loop gain must be less than 1. Okay, so this is like highly celebrated as a DC loop gain condition. Here you may have a little bit difficulty in reading this condition, why I have written the lambda max, because it is nothing but the DC loop gain N0 M0, but it is this is technically correct or mathematically correct only for CISO setting. Okay, if it is MIMO, then the gains are not scalar gains, they are matrix. So that's why that is if we have to quantify the value of a matrix, then of course that is we have to either we have to describe it in terms of its eigenvalues or in terms of its singular values. So usually in the papers like they do it with respect to the eigenvalues, and since it is about the maximum gain, so that's why the condition is given lambda max of N0 M0 less than 1. Let's see a few examples, then it would be clear. Here I have taken three varieties of example. One is a stable NI system, this one. Another one, we have a NI system where we have the poles on the j omega axis but not on the origin. And another one, that is where I have two poles on the j omega axis but not on the origin. Okay, all of them are NI system provided the first one is asymptotically stable, but the other two are marginally stable, right? It is not unstable, they are marginally stable. And you see, the beauty of this stability result is that all of them can be stabilized by the same controller, 1 by s plus 5. Not only that, there can be like many choices. Then that's you would be like pretty surprised, and of course you would be asking me that is how it is possible that is one controller can stabilize all these three plants, but at the same time you are saying that is there can be this many other choices. Only thing is that is if you just see the stability result once again, the positive feedback interconnection of an NI system and an SNI system is asymptotically stable if and only if the DC loop gain is less than 1. That is the main criteria. That is the stability condition. It depends only on the zero frequency gain condition. And because of this particular property, this theory has become really popular with respect to the other ones. Not everywhere, but at least if you have some practical systems which satisfy a negative imaginary property, for which designing the SNI controller is really like the easy matter. Why? Because you can easily find out the DC gain of the plant, and accordingly you can think about a simple SNI controller and you choose the pole 0 so that the DC loop gain less than 1, this condition can be satisfied. What I just said, that means suppose you consider this a stable NI transfer function, what will be its DC gain? You make all the S quantities to be 0, then the numerator it will be 1, and the denominator it will be 1 into 5. So as a whole, this is 1 by 5, right? So that is here, that is if you would take another controller, that is where that it would be less than 1. So accordingly, that is 1 by S plus 5, that will work. Or even that is if you want to let's make the stability bound, that is the quite better, then you can even reduce that pole. But compared to the other two cases, if you see that what is the steady state gain or even what is the zero frequency gain, you put S equals to 0. In this case, it will be 1. So 1 into this one will always be less than 1. For the other case, again, it will be that is the 2 into this, and accordingly, even that is here, if you find that it is coming to a very close border, you can always change the values. Okay. So what is the takeaway point? That is, as we know, that is for stability, we need M0 less than 1. So once the plant is given, that means M0 is known to us. Accordingly, you design a SNI controller so that M0 less than 1. That is one of the main advantage of NI theory. Then the second part is that if you have a NI system with poles on the origin, say for example 1 by S or 1 by S square, then what will be the SNI condition? Here, of course, you might argue that is, sir, we have already like understood one case, that is this the first case. Why can't the second case, which I'm just about to start, cannot be accommodated by the first one? Because here you see the stability condition is M0 into N0 less than 1. So the N of 0 or M of 0, they must exist. If you have a system or if you have a transfer function having a pole on the origin, simply suppose 1 by S or 1 by S square, what will happen if you put S equals to 0? Simply it will become undefined or infinity. So that means for the systems having poles on the origin, the zero frequency gain is not defined. So that's why this version of the stability result cannot be applied to the NI systems which has a poles on the origin. So for them, we have a different version, which is now, that's why the case 2 is a separate one from case 1. For them, the stability result is only the stability result relies only on the controller. That is, provided you have a NI system with a single or two poles of the origin, because it cannot accept more than two poles at the origin. The internal stability condition or the closed loop stability condition will be that is the controller must have a negative DC gain. Okay. So now I think you can relate. That is the two examples which I showed earlier. That is one with respect to the single integrator, another with respect to double integrator, and which that is at that time I mentioned that is the by negative imaginary theory it can be like tackled. Now you can like relate. That is why I mentioned that, because so with this free example you can see that is here again I am considering that is K by S. This is a NI plant with a single pole origin, another similar NI plant with a single pole origin, but one more pole and zeros. Here you have a double pole at the origin. Each one of them can be stabilized by an SNI controller of simply a first order biproper SNI controller of the structure minus of S plus Z by S plus P, with the condition that the 0 greater than Z, Z 0 less than Z less than P. That means the pole of this controller must be placed beyond the 0. So the 0 is closer to the origin compared to pole with that particular setting, and the minus is there so that the controller DC gain can become negative. Okay, so the N0 less than 0 is satisfied. So this simple controller structure, a simple first order controller, can stabilize all these kind of all these three systems. Okay, and here please don't think that is the negative imaginary theory is restricted to only first order, second order, or third order systems here. Only for the like simplicity of our presentation, that is, I am showing the simple examples, but it is applicable to any other system. Okay, this is just for the sake of like simplicity. I am showing the very simple examples. Now, a robust stability application, that is, if you remember, that is what the control algorithms or the stability techniques we learned in our undergraduate, even in MTech days. Starting from the Routh-Hurwitz, Bode, root locus, Nyquist, all those things. But we really face difficulties. That is, once a precise transfer function is not given to us. That means if you have a transfer function which has some of its elements or parameters varying in a range, that is, instead of being a fixed parameter, suppose you have a ni plant 1 by a square plus as plus b, where a and b, these two parameters like vary in the range 1 to 10 or 0.1 to 1, then can I design, or then can this theory be applicable? Yes, in that case also the theory will remain applicable. How? Because although here the parameters like vary in the range, but we can theoretically prove that this structure 1 by a square plus as plus b, they will remain ni for any positive variation of its parameters a and b. Okay, so now accordingly we can design one SNI controller so that the ultimately our objective is that we have to object our the condition is we have to design the SNI controller so that the loop gain at the zero frequency should be less than 1, right? So here what is the DC gain of the plant? You make the all the S quantities 0, so it would be 1 by B. But now B is not a fixed quantity. B varies in the range 0.1 to 1. So what will be the maximum value of the 1 by B? So of course it would be 1 by B minimum. So 1 by 0.1, which would be 10. So if we can design, or if we can choose an SNI controller having a DC gain so that the product will always be less than 1, honestly speaking, I have chosen the SNI controller, the pole at -15 with respect to this, considering the same reason, that is the maximum gain which the plant can offer will be 1 by B minimum, which is 10. So if I take an SNI controller 1 by S plus 15, so the product of the DC gains of the plant and the controller would be less than 1. So with that simple condition, you see the stability result, or I mean the NI SNI stability result, is not only applicable to the normal LTI, to the normal LTI systems, but also it can become a robust stability result, right? I have also tested the step response corresponding to different, that is A and B values. Everywhere you can check that is the response is stable. Okay. So then the question is that is we have already like learned the basics of the NI theory, and now it is known to us that is there is one class of LTI systems which is called negative imaginary systems, and what properties they satisfy, that too we have come to know their stability result, and also there is there the stability condition simply depends on the DC loop gain, and that is the reason why that is it can be applicable in many systems where only the DC gain measurement will make the system like possible to work in practice. For in such kind of cases, this theory can really become useful. But now the question is that since we have been dealing with the multi-agent system, can NI theory be extended to multi-agent setting? That is a big question, right? Yeah, this slide says yes, that is also possible. How? If a unit system is ni, that means suppose m is one unit, the agent of the dynamics of one agent, if that is ni, then the whole subsystem, that is this plant block and the and with the network block, it will also this remain, it will also retain the ni property. And if one unit is SNI, then the whole system will remain SNI property, will retain its SNI property. It can be like proved theoretically. And the condition is if we deal with the multi-agent systems on undirected graph, then it must be connected. And if we deal with directed graph, then it must have a spanning tree. Under both the situations, we can prove that provided the one single the agents are ni, their whole multi-agent combination will also be ni. Or if it is SNI, then the whole multi-agent combination will be SNI. If it is so, then actually one big headache will go off, because if the network version retains the same property, then we are just going to bring a distributed SNI controller, and then again our the whole block diagram will become a like the block of the feedback interconnection of two block like this. That is, you have a multi-agent plant and then you have the network block. So easily you can club the network block with either the plant or the controller. And as we have just seen, that is, if an individual agent, if an unit is NI or SNI, then the whole multi-agent representation or the whole multi-agent system will also remain NI or SNI, provided the graph satisfy those properties. Then we can easily decide this SNI controller by looking at the DC loop gain condition, because anyway the DC loop gain condition will be the prevalent whether it's a CISO or MIMO case. Okay, so that is the main motivation behind using the NI or behind designing NI based distributed control scheme. So if you ask me, that is what will be the choice of the SNI controller, then here I'm going to mention three specific cases. I hope it would be like the easier and exhaustive for us to consider different scenarios. First choice, think about if the plant MS is a stable NI or SNI systems with positive DC gain. Okay, because most of the practical system are positive. For them, we'll have to use an unconventional negative feedback scheme. Why did I say unconventional? Because usually NI systems are stabilized in a positive feedback mode, but they can work with negative feedback mode also. Or in these particular cases, I mean, if you have to design or if you have to achieve a cooperative control for the NI systems having positive definite DC gain, then you have to choose an SNI system, or rather that is it must be an NI, because SNI cannot, this is, please just excuse me for the typo. Whenever your plant is a stable NI or SNI, you have to choose an NI plant. That means the strictness anyway won't be there because it is going to contain a pole at the origin. And the reason behind, ultimately we know that is if the steady state error has to be nullified, we need at least one integrator into the system, right? That is again that is we learned in our classical control, that is if the steady state error needs to be zero, we need an integral controller. That means in the loop you have at least one integrator. Okay, so if the plant becomes stable NI or SNI, that means there is no question of an integrator, no question of the pole at the origin. So the controller must be an NI system with a pole at the origin. So here again, I'd like to that is to tell you, please don't think that is the plant means it will always be NI and the controller means always be SNI. It is about a feedback interconnection. One of them will be NI, another one of them would be SNI. Okay. The plant can also be SNI and the controller can be NI. It is not that the plant will always be NI and the controller will always be SNI. Okay. So the second one is that if the plant is stable NI or SNI, but its DC gain is negative, it can happen. Although those type of cases will be very rare, but still it can be a possibility. In that case, we'll have to choose an NI controller. Again, like please don't mind for the typo. It is not an SNI, it should be the NI. Okay. We have to choose an NI controller with a pole at the origin, because otherwise we cannot nullify the steady state error. And ultimately remaining consensus means we have already seen that the steady state error must, the zeta t must go to zero. For that we need one integrator in the loop, that is one pole at the origin. So if the plant doesn't contribute any pole at the origin, you have to choose a controller which will give us a pole at the origin. Otherwise we cannot show that the steady state error is going to zero. But in that case, the positive feedback scheme will be required, because here the plant is having the negative definite DC gain. And lastly, if you have the plant is a NI with one or two poles at the origin, then you can easily remember the stability result. You need an SNI controller. In this case, it is the controller is SNI because the plant you are considering that has the poles at the origin. So the plant is marginally stable, and then the controller would be SNI having a negative DC gain. These three type of cases may occur, and by which we can design or we can cater to most of the scenarios. Okay. Now I'm coming to the last part, that the application part. Basically, first of all, it is application to control of mobile robots. So this kind of like small two-wheel mobile robots. Of course, this is not self-balanced. It has a dummy wheel at the front. So this is like stable in nature. So now, if the question is that you have a group of mobile robots, as you have seen in the first video, that is suppose this is basically the same mobile robot. The name is Mona. It's the name which has been given by its like the developers. It was an autonomous miniature mobile robot. It was developed in the University of Manchester. And there was a researcher, Dr. Fasha Darwin. That is, he was from the robotics department. Although he is now in Durham, he was originally in Manchester. That is, he like developed this particular small mobile robot during his like PhD. This is a very a good resource for doing experiment on the cooperative control or even for on swarm robotics. So the video that you have seen there, we used this Mona robot only. Now you must be inquisitive about its modeling, right? So you might be knowing that is those who are working in robotics or even the control, that the kinematics of a unicycle is always given by this. It is the x dot equals to vi cos theta, x y dot equals to vi sin theta, which I have noted here by x. That means the displacement along x-axis, x suffix y means displacement along y-axis, and theta means theta dot means the rate of change of the heading angle. Okay. Now it's a nonlinear model. We cannot directly apply the cooperative control law that we have learned because it's a NI cooperative control law. So if you have to apply the NI principle, then it must be LTI because so far we haven't learned the nonlinear negative imaginary theory. So in this case, that is everybody is about to be like very afraid. That is are we going to stuck? And no, actually here we are just going to apply one hack, and that hack is that ultimately we would be like proposing a two-loop control scheme where the inner loop would be a feedback linearizing control scheme. Feedback linearization is a technique which not only stabilizes a nonlinear system, but at the same time, that is, it gives us a reduced order linear mapping. Okay, so here I have this for the sake of completeness, I have included the steps, but please don't worry about the steps. Like you can just look into it later. With the feedback linearizing control law UI, which will be of this fashion, if you plug it into the system, then ultimately it will give us a two input two output double integrator system. This is the reason why right from the beginning I have been emphasizing on the integrator dynamics, whether it's a single integrator or double integrator. Especially double integrator has a lot of application because as I was like talking about the last day also, whenever we think about the motion of a system, then at least like the steady part of the motion, I request the participants to like put off their microphone because it is causing some disturbance. Okay, whoever has switched on his microphone, please switch it off. So here you can see that it's a two input, two output double integrator system. Okay. Now you can think about that. We have already understood the NI theory. We have seen that is the NI based control scheme can be easily developed. It can be extended to the multi-agent setting. So if we can think about a two loop control scheme where the inner loop would be the inner loop will deploy the feedback linearizing controller, and the mapping from this point, like where I'm now hovering the mouse, like the input to the this red dotted block to the output of the robot kinematic model. So that model or that mapping will be a reduced order linear mapping, which is nothing but 1 by a square 0 0 1 by a square. I mean the T2 double integrator. Okay. So when we now that is if the question is how will we design the control scheme? So we are just well equipped. That is, we have already learned the NI-based controller, but the only problem was that if the original plant is nonlinear, then we don't know how to apply the NI theory because so far we don't know the nonlinear NI theory. So to circumvent this problem that is here, we are applying another controller, which is not only a controller, it also gives us a reduced order mapping. So now essentially the whole thing has become a two-loop control scheme where the inner loop applies a feedback linearizing controller and the outer loop it acts as a like the upper level controller or the super level controller, which will give us this distributed controller and which will be responsible for achieving the consensus. Here if it is a robot agents, then of course they are more, we have to just consider we need to know the positions. So if you think about or especially the arena that we used in the video, there you might have seen the all the robots were just flying on a glass board. So actually in the top it was there we had a overhead camera with by the overhead camera we can capture the like position of the mobile robots. But here I would like to mention again, that is, a camera is not always required. If you do your experiment with the expensive robots equipped with onboard mobile camera and all other processing units, then directly these robots, even without camera, if it has a lidar, then it can find out the distance with respect to its neighboring agent, and in that way we can like remove the overhead camera, and the algorithm can be implemented in a fully distributed manner. What we did in our experiment, that was the theory was developed for the completely in the distributed for distributed systems, or in the theory is the controller theory that we developed. It was fully distributed, but so during the experiment, since we didn't have the expensive mobile robots with with the camera, so then we cannot use those. Sorry, it didn't. We'll meet tomorrow. Okay. 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 Sure. So here, that is, once it is done, that is from the outer loop, we can always do it in the sense by applying the NI control law. And then again, we initial after this, that is, I will like show you that once it is a UVV, for the UGV, it is fine. There was one more video. I'm just not playing it as of now. I'm just going to the cooperative control of UAVs. Okay. There, that is, you would be, this part is going to be very interesting one, and which is the main theme of like today's presentation. Although I didn't change the title of the talk, but it was originally for how we can implement or how we can utilize this cooperative control scheme for border security surveillance, right? So essentially, it is nothing but, suppose you have two or three subgroup of the mobiles, okay, subgroup of this drones equipped with mobile cameras for mapping the area. Now, for different region, that is geographically in different places, like you have, that is a number of subgroups. Okay. So here, if you consider this particular scenario, that is, you have, that is, three subgroup. The first one, it has like four drones. The second one, it has three drones. The third one, it has like again three drones. Okay. Now, that is certainly, that is, they have seen, or like they have detected the existence of enemy or hostile drone. So here, this slide, it gives the idea of the enemy drone cordoning and monitoring. From the terms cordoning and monitoring, you can easily understand that is, suppose in the parliament, you can easily like remember that in 2001, or I think that there when, or maybe in 98, when our parliament was attacked by the militants. So it is not always possible for the human sentries or the human guard to, that is, inspect each and every like a nook and corner of a very huge building. But instead, in addition to the, there's a human surveillance, if we can like apply, or if we can just employ automated surveillance or autonomous surveillance, then it can really, that is, it can do a lot, right? So in that way, there the concept is that if you have the multiple, like suppose in one floor you have like two three different groups, in another floor you have again different groups, so ultimately there would be the intergroup communication and intragroup communication here. From that is the main idea. If this is the situation, then that is, how can we design the whole thing, and can we still apply the NI theory for this particular condition? That is, yes, in this case also we can apply the NI based theory. That is, that in the video already, that is, we have shown that one, that is the multi-group, or the subgroup, two subgroups were there. If you remember, that is in the second video, we started with the first part of the experiment was on one drone. Sorry, was on only one subgroup containing four drones. And the second part of the experiment, it had two subgroups, each containing three drones, right? This is basically the same thing, that is with respect to there. That is, now, that is, I'm going to show you a very interesting video by which, for the time being, if you see this particular snapshot, this is like the snapshot has been taken from the experiment only. That is, suppose the blue ones, they are the leader drones, and in a particular room or even in a particular region, some stranded people are there, and there are some drones or there are some rescuers who are trying to like rescue those stranded people, or like stranded like passengers. Okay, so in that way, we will find that is these blue ones, they will form a 3D formation, and gradually they will try to bring the trapped ones inside them, that as if the leaders are coordinating or then safely navigating the stranded passengers from the maybe it's during the natural calamities or earthquake devastated areas. If the people are unfortunately stranded, then these drones can go to a certain place and they can safely they can safely evacuate those people. Okay, so idea was basically that only, and it is the technically speaking, it is its operation is called search and rescue operation. Here also the similar kind of two-loop distributed control scheme will be applied. That is the inner loop. There will be one inner loop control scheme because that you, as you know, there is the UAV or the drone dynamics and the kinematics. They are non-linear, so we cannot directly apply the NI-based control law. So first we need a feedback linearizing control law to get a reduced order linear mapping. Here it would be three input, three output double integrated a square 0, 0, 0, 1 by a square. So three input, three output double integrator system because now it has three channels X, Y, Z. And then the outer loop controller will be responsible for achieving the formation or consensus, whatever. So in that way, the same kind of configuration or same kind of arrangement would be used. Even in this case, let's see the what is the video. I hope after this video, it would be like very clear and you will enjoy. I hope the video that you can see the video. If there is any problem, please feel free to mention. I will disconnect and like share again.
Video is visible.
Okay, thank you. So it is about the kind of a search and rescue operation. And also now you are going to witness this 3D formation. Earlier we saw only 2D formation. Sorry. Here actually I wanted to like the pause the video because like this is the snapshot that is which I showed you just 2 slides back. If you see that this is a pyramid type formation, right? This is a 3D formation. And now that is you can count that it suppose this is leader 1, L1, L2, L3, L4, and L5. So these five are the leaders or the rescuers. As if they are the rescuers, and these two which are in between, they are the stranded people or the stranded passengers. So once these leaders or the rescuers, they can form this group, or even they can just form a region, and if they can that is get or if they can contain the stranded passengers into the safe region spanned by these leaders, and accordingly these the rescuers they will flow from that the place to the safer place, and accordingly like they will guide the stranded passengers to navigate through this the problematic zone to the safer zone. So that is basically the idea behind the search and rescue. So the rescuers are nothing but the leaders. So in terms of cooperative control, we say the leaders and the followers. Here the followers are the stranded passengers you can think about, and the leaders are the rescuers. So as if in a earthquake devastated area or during some natural calamities, there are some people they are stranded, there is no help, so we are sending the drones to first locate them and then to guide them to safely evacuate from that area to a safer zone. Okay, that is basically the idea. And the other video that you have seen at the beginning on drones, there you saw only a second order, sorry, there you saw only the two-dimensional formation control, right? That means it is restricted one plane only. But now it is a three-dimensional. But in the subsequently you will find that is the top one. If it is faulty, then this 3D formation will break, but the mission that is won't collapse. With the healthy ones, it will still continue. That will be one of the main strength of the this cooperative control scheme, that even if some of the agents become faulty or if they just go out of the network, but still the healthy ones will reconfigure themselves, and that too it will be a autonomous reconfiguration, and the mission will continue. Okay. So with that, that is, you can also apply the same scheme for controlling the underwater autonomous vehicles, AUVs, although I'm not going into detail. The same kind of thing, that is where we were talking about the security surveillance. The same kind of security surveillance we can think underwater also, where the if any enemy submarine is there, then a similar kind of thing with our Indian Navy is also attempting. In fact, they have already have this kind of systems which they have imported from the foreign, some of the foreign countries. So in that respect, the same kind of configuration or same kind of control scheme can be applied also in, like, although in underwater we have different set of other challenges, but the control scheme will remain the same. I mean, the cooperative control and the agent, whatever we have discussed and learned so far, they will be applicable. The only difference would be that is how we will configure the distance between like two objects underwater. That will be different, and like that will be and to some extent problematic, but those things are not part of our representation. With that, I'm just to conclude finishing my talk. And just I always like acknowledge, and I always like acknowledge my team. That is, starting from Mr. Vishwanath Pal, he is the senior most in my team, as Vishwanath and Athoibi. After that, Nitisha is also working on the same topic. I mean, all of them are working on like different applications of cooperative control. Some of them are working on the application, some of them on theory building with different type of like systems. And like in fact, the last two students, they are already passed out. So with that, I finally like thank all the participants and the organizers as well for just giving me the 2 sessions to discuss all the things. I hope the participants have also enjoyed. Also, like maybe like most of us are not from the control background, but at least that you have understood that is these kind of systems do exist. And if we wish, that is then a lot of interdisciplinary research can be done. That was my main motto. I know that is we have this the audience coming from different background, but the only thing is that is whether you are from CAC or EC or E or ME, there is the ultimately thing is that these are all kind of interdisciplinary research areas where really that is each discipline can that is contribute. With that, this I'm concluding my talk, and if some of you are interested, then please feel free to discuss with me later. You can always like reach me out through email. So, okay, now that if you have any question, please feel free to ask. Hello.
Good
Uh,
afternoon, Dr. Parijat.
yes, madam, I just finished. Yeah.
Yes, yes. Okay, dear participants, so we have a wonderful session with Dr. Parijat. So if you have any queries, then you can feel free to ask questions.
Yes, if you have any question, please feel free to ask. And even that is like I will share my slides. Don't worry. That is after this, like it's a 6 days wide FDP. So maybe there is you were a little bit occupied. There is many things you have learned or you have gone through during these last 5 days. So after that, you like take a pause and you start again. As if you have like any doubt or queries, please feel free to approach me. I would be more than happy to discuss. And this is one area that is which is relatively new, because the control is like most of the researchers, they don't wish to come to control because it is one of the like most mathematically involved field, and also there are so many results and already saturated. But there are many interdisciplinary topics coming on like based on control, especially this robotics. It emerged from control only, but there that is like you have a lot of chance to work on. It is not that control is completely saturated. Yes, the core control is more or less saturated. even the problems which are still there, it is very difficult to work because it needs a lot of mathematical tools, and we engineers, we don't have that much of like core mathematics background because we are never from pure maths background. So that's why it is always very challenging to work in theoretical control. But you won't believe that is that the control has applications in each and every engineering discipline. Whether you are from CSE, EC, mechanical, aerospace, everywhere there are applications in control. And the CSE people, they are doing really good in robotics, because in robotics there is a such a scheme that is there. If you have to run a robot, then the software part or even the coding part, it forms the major component. Of course the control will be required, because when the motion and navigation is to be controlled, then we would need control. So but anyway, that's why it is one of the very interesting and vibrant interdisciplinary research area. So I insist with all the like, participants, that is you also like think in the different like dimension, like rather than whatever that is you are doing at this moment, that is always for our better survival or for like publishing more papers, you have to branch out, that is you have to upgrade yourself. So that is try to just come out of your comfort zone and you think a little bit just beyond your comfort zone. And I believe this at the end it would be a win-win situation. And I believe this is the same thing for all the like the faculty members, whoever, that is for all of us, that is whatever we learned or did during our PhD time. Then after that we had to migrate. That is we or even may not migrate completely, but we had to start new things, because otherwise how will you guide your students, right? So with that, that is I encourage and insist all of you, and really that is I'm like thankful to the organizers for giving me the chance, especially for like 2 sessions. And today that is I could complete. Yes, I know that is I couldn't just get into the all detail, but at least that is I could finish whatever I planned on the first day. Thank you, Dr. Anuradha, and to Pratusha as well.
Thank you so much. Thank you so much, Dr. Parijat. Um, yes, yes, Pratusha. Actually, Dr. Parijat's exploration of the evolving landscape of military surveillance through drone technology is simply fascinating and thought-provoking. So you have skillfully guided us through the intricacies of modern surveillance techniques and
Thank you so much.
also highlighting the technological advancement also operational strategies and the multifaceted challenges that comes within, and also your insights into the real world application and the potential impact of drone technology in enhancing security were especially compelling. The way you address the challenges of implementing these technologies, so this is something which really participants, I'm sure, enjoyed a lot. And your passion for the subject and your ability to distill complex concepts into such accessible knowledge are truly inspiring. So I hope all the participants
Thanks you a
have
lot. I'm
truly,
really
truly
honored.
enjoyed.
It is truly my honor.
So, on behalf of everyone here, I extend our deepest appreciation and hope that we can continue to learn from your insights in the future. So, thank you very much, Dr. Parijat, for a truly engaging and enlightening session.
Thank you. Thank you. And
So,
have a nice
I
evening, everyone.
yes, I just want to take the 2 to 3 minutes so that I can
After
request.
that, I think the second session will
The
start,
second
right?
session will be started. Yes, Dr. Probisha. Dr. Probisha is waiting for us, and I am just want to take 2 to 3 minutes from the participants so that they can turn on their camera so that we can take the attendance for this session. So, participants, please turn on your camera.
Okay. So there's I'm leaving. Okay.
No, no, no. You just please stay with
Oh,
us,
okay,
Dr.
okay,
I'm
okay.
just requesting. I'm just taking 2 to 3 minutes only.
Yeah, yeah, sure, sure. No problem at all.
Thank you so much.
Thank you. Thank you. So you also
Thank you
take
so
a
much.
break because it is really that is hectic for you and Pratusha to manage all the things, and it has been really engaging for the last 10 days. So I
Yes,
can
yes, but
understand that
it's
is
it's
how much
it's uh,
responsibilities you both have taken.
yeah, it's our responsibility, but at the same time, we are enjoying a lot because we have got the opportunity also to listen from you and the other speakers as well. So, dear participants, we are just taking 2 to 3 minutes break so that we can process this session. And yes, I also welcome Dr. Provisha because I can see you that you are rightly here with us. So we are taking just 2 to 3 minutes break so that we can start your session as soon as possible. So dear participants, don't go anywhere and stay tuned. And we are just, starting the next session. Thank you so much.
Okay, bye, bye. Yeah.